Okay, I'd like to welcome our third presenter, Sean Clifton. He is a senior principal at Magnusson and Klemencic Associates in Seattle, Washington. He's a leader in MKA's efforts in Southeast Asia and throughout North America, an experienced engineer in both high-rise and performance-based design towers, having personally led design of over 50 high-rise projects. Sean has a passion for efficient and cost-effective structures that realize the project goals and architectural vision. So please join me in welcoming Sean.
Thank you all. Thank you to the committee for inviting me to speak today. I'm really glad to see all of the JCI attendees. So today I'm going to be talking a bit about performance-based wind design, which really does have, I think, some good parallels to design applications in Japan, given both the high seismic area and also the typhoon region that some parts of Japan are in. So while I haven't personally designed anything in Japan yet, I've been doing a lot of work in the Philippines, which is also very apt because it's high seismic and high wind. So we're going to be talking about performance-based wind design, which is really an extension of performance-based seismic design that we've been doing in the United States and throughout the world for the past maybe 20, 25 years now. So what we're using as our kind of guidelines and go by at this moment is what's called a pre-standard that ASCE put out back in 2019. This was put together by really a collaboration of practicing engineers, wind tunnel engineers, local authorities, city officials, academics, and kind of collaborated to develop at least an initial set of guidelines of how one might approach performance-based wind design. Since 2019, it just recently got updated, this standard, with some additional inputs and tweaks that we've been providing to them throughout the process of what we've been learning. In addition to that, ASCE, which is really our standard for buildings, in 722, the most recent guidelines, actually does reference performance-based wind procedures as an acceptable procedure for designing buildings. So at a high level, what this pre-standard does and when we say performance-based wind design, what are we talking about? So there's only three critical areas of the building that we consider when we do performance-based wind design. There's occupant comfort, which we normally consider as acceleration of the building. There's operational performance, which kind of simply is known as drift, making sure that drift limits are met. And then there's what we call continuous occupancy performance objective, which really is the strength of the building. Make sure that the building is suitable in a strength level event. And we do a rigorous evaluation on these three topics, kind of going through making sure different criteria are met and then revising the design if necessary. The focus, really the unique aspect here, is mostly in the strength design component. How do we design the building for strength? And there's a number of different methods listed here that we use to evaluate this, with the most common and easy to implement one is using a time history response analysis. So I'm going to use the majority of my time here today to actually talk about a real project that we recently went through this process on and is now being built. This is a project that we started in 2021 in Austin, Texas, being co-developed by a developer Tishman Speyer and Ryan Companies. The architect for this project is Handel here in San Francisco and Page Sutherland Page in Austin. So this project is called 321 West 6th Street. It doesn't have any exciting name yet, but it's a 58-story tower, about a little over 200 meters tall. All concrete shear walls with concrete outriggers, and then a larger cell in the lower portions of the building. It's a mixed-use building, so it's mostly residential at the upper stories, with then some office component and parking component at the bottom. So when we first got involved in this project, as we do with most of our tall buildings such as this, one of the first things we did was went into the wind tunnel. So we went into the wind tunnel with a CPP in Fort Collins, Colorado as our wind tunnel consultant. And they tested our geometry of our building within the surrounding context of Austin, downtown Austin. When we started to get the results back, we saw some increases in the loads, really looking at some of the dynamic aspects right here at this wind angle coming from about 110 degrees off of north, where we were getting what we call crosswind effect. The wind hitting the building in one direction, causing the building to oscillate in the other direction. Similarly, we saw another higher than typical response coming from a different wind angle as well. When we looked at what this result meant, this is a plot that shows in green here what the code would predict, what ASCE 7 would generally predict. And then in yellow is the results of our wind tunnel, looking at just the base overturning forces in the predominant directions. These increases were in the order of 20 to 30% from the code. And we're scratching our head trying to find ways to how do we mitigate some of this impact, because we knew it was going to impact the design of the project, increase the costs, and the developer turned to us to say, what else can we do? And that's where we brought up the idea of performance-based wind design. Before this project was done, there hadn't been a project in the United States that actually implemented this pre-standard as of yet. So it was all very, very new at the time. But working with the client team, the wind tunnel engineer, we went to the city of Austin and pitched this idea. And they were very receptive, and we immediately got a peer review panel engaged consisting of Walter P. Moore and RWDI as our peer reviewers. As we started to go into the detailed aspects of it, we looked at these three primary design criteria. Looked at acceleration, we looked at drift, and we looked at strength. Luckily, the acceleration performance was met. So here our red line, many of you have probably seen plots like this where the return period is on the bottom and our resulting acceleration on the vertical axis. And we did meet our performance objectives by a reasonable amount on the acceleration. When it came to drift, the pre-standard recommends a little bit more detailed methodology for evaluating a building drift, and what they call a deformation damage index procedure, which rather than just using simple drift, just taking the story displacement above and below and seeing how much that drift results in, we actually put in panels around the building on the exterior and the interior to more explicitly evaluate the shear deformations of those panels. This was our result. So on the left plot is the x-axis, the right plot is the y-axis, and you can see the solid lines are the kind of DDI approach, the drift that we get, with the dashed line being the simple drift. So a similar answer, but we still found that there were a bit higher drifts reported, but still meeting the acceptance criteria outlined for the curtain wall deformation or the interior partition deformation. So we knew we were okay on the drift side. Next, we went into the fun, more challenging aspect, is really the strength evaluation and looking at a time history response. So when we do a time history response, we actually work with the wind tunnel engineers to identify certain wind angles, the 110 and the 60 being the most critical, and run a 1 hour long windstorm in our analysis to actually report what the resulting forces and deformations are in the building. So what you're seeing on this plot, this is, again, a base overturning moment plot in the X and the Y, with the yellow line being what just a regular wind tunnel static approach would give you. If you were just put static loads in the building, see what the demands at the base are, that's what the yellow is. The pink lines is the results of a 1 hour long time history from the same storm running over and over and over. We like to call this the spaghetti plot. And in this case, we actually did find, just doing a linear time history analysis, we found that in both the 110 and we also evaluated this at the 60, we found some excursions where that demand actually exceeded that envelope, which is a bit unusual because it's the same level of demand. There shouldn't be an excursion. And this is something that we worked back and forth with the wind tunnel engineer to try to evaluate why are we getting the response of the building to actually exceed what a static approach would already tell you. This is one of the things that is anytime you implement something new, you learn new things. And this is one of the things that we found that was a bit surprising to us to see this excursion. But nevertheless, we continued down this process and looked to how do we improve the design of this building. So the pre-standard, really what we're doing when we do this approach is we're allowing some very modest yielding to happen in certain components of the building, of our lateral system. Really focused on those components that we can easily predict the response of, similar to what we do in seismic design, where we allow certain components of the building in seismic design to actually yield and dissipate energy. So the pre-standard allows you to do that up to a demand to capacity ratio of 1.25. And this also allows us to take advantage of some of the expected material strengths. We know our concrete's going to be stronger than our specified. We know our rebar is going to be a little stronger than specified. So we can get a little bit more benefit out of it. And similarly, we do have minimums that we have to meet. So we use the code-based procedures to calculate a lower bound. But this does allow us to effectively take some of the rebar out of the design and then verify the performance. So the particular components for our concrete shear wall building that we're focused on is the coupling beams and then the shear walls themselves. So for the what we call deformation controlled elements, the ones that we know how to predict their behavior, we actually allow these components to slightly yield and use that 1.25 DCR ratio. For the components that we don't want to see yield, the shear wall shear and coupling beam shear, those we don't do that same approach. And we check the demands rather than using this approach. So after we've gone and redesigned the structural elements for that kind of optimized design demand to capacity ratio, we then build a very complex nonlinear model. We actually used ETABS in this case to do this more complex nonlinear model where the coupling beam elements and the vertical PMM panels in the walls we model with nonlinear properties. So shear hinges for the coupling beams and fibers for the PMM sections. In order to do all this, though, we had to really correlate the behavior with real physical testing. So we've done a number of different tests. One of the most useful ones we did was actually at UCLA, where we had them do physical testing on link beams, but using a wind loading protocol as opposed to a seismic loading protocol. There's been many, many, many tests done using seismic loading, but wind loading is a very different type of loading where we have a lot of very small cycles and very few big cycles. So we actually went through the process of doing this testing and then using the results of that testing, calibrated our analysis model, those hinged properties, to reflect the behavior that we observed in the testing. So this is the result of that calibration. We call this a backbone curve, where we've established the behavior of that beam up to a defined yield point here for that section. The yield point here is very important because that's ultimately how we classify or check the deformation response to ensure that it meets the criteria. This is one of the things I think ACI and the concrete community is going to be doing a lot of work on in the future because there's a lot more research to be done on this topic and really what is appropriate acceptance criteria and modeling practices. So there's already some other research ongoing right now on this topic. So we take all of that, we build this very, very complex model, and then we press run, and we hope it works. And of course, we found out it didn't work a few times. We had some back and forth, back and forth. Eventually, we got the model running smoothly. And in this case, we actually ran 5 wind angles, 5 different angles, 1 hour storm at a time, oftentimes running in parallel. And it took 1 month of analysis time. I mean, each 1 hour windstorm is 35,000 steps. You can imagine a nonlinear model taking a long time, much, much different than seismic, because those tend to be in the thousands of steps, not tens of thousands of steps. So that was a learning experience for us. Our client was a little nervous, but luckily we managed to actually get it and get really good results to not end up impacting the schedule. And subsequent studies we've done, we've found ways to improve some of that runtime, but it's definitely been a hurdle in the process early on is the waiting game on the runtime. But in the end, we get results that look something like this. So this is that same plot I showed you earlier with the yellow being the static load evaluation. The pink kind of behind is the linear time history, with then the blue is the nonlinear time history. So it's hard to, there's so many lines, it's hard to make sense of it. But in general, you'll see that the blue is smaller than the pink. Really, this is because it's capturing some of that supplemental damping, additional energy dissipation that's happening through some of the nonlinear behavior. When we actually extract that kind of cumulative energy plots out of SAP, you'll see, we can see that in the green here, this is some of the hysteretic damping that you get from some very modest yielding that we're seeing in some of these components. Once we dive deep into those components and actually say, well, what do the actual numbers look like? When we look at coupling beam, the rotation of coupling beams, we find very, very modest yielding in the range of just a few cycles. So here, this is for our conventionally reinforced coupling beam. This dashed line is the yield point that we've defined. Only a few beams go past that yield point in this case. When we can kind of dive in deeper, we look at it, we extract, when we looked at one beam, we see that hysteresis performance. And then we go down and this is through the length of time, we go down and count. We found 3 cycles where that beam actually went post-yield. So very much within the criteria we established early on. Similarly, when we looked at the walls, the PMM response of the walls, we found very modest wall strains, and we didn't even get to yield. Even though we designed intending there to be yield, we didn't even get to yield because the overall response was somewhat reduced because of the energy dissipation we saw. So fortunately, even after that month of runtime, all the results were good. We didn't even have to go back and change the design. We didn't have to iterate on changing components in this example. So the punchline, at least for the clients was concerned, is the resulting material savings. We saved somewhere on the order of 20 trucks of rebar, 10 trucks of structural steel because we had composite link beams, and about 200 trucks of concrete trucks. All in resulting in around a 5% structural cost savings as opposed to the baseline design. So it's a fairly modest number. Given this was the first one, we kind of knew that it was going to be on the smaller side, but we know there's a lot of opportunities to push this a little further as we learn more and get smarter about how we approach this process. But the client was happy at the end of the day that we did help mitigate some of the higher than code expected loads. So there's been a number of articles written about the project. Engineering News Record is one of our big publications that we have and wrote a story about this. And now it's in construction in Austin, Texas, up to about the 12th floor, so moving up. So there was one other aspect of this I wanted to touch on briefly is the pre-standard outlines a few different ways to go about this verification. There's the nonlinear time history response direction that we took, which is very much well understood, well established. It's what we use in performance-based seismic design for many, many years. The other approach is more of actually targeting a specific reliability. If you open up ASCE and you go to the first chapter, there's this table 1.31, which talks about the target reliability depending upon your category of building, which really is the underpinning for all of the rest of the code. Most people don't understand this. I'll be honest, I don't fully understand this table. But some really smart researchers have tried to take this approach and develop a methodology for how you might evaluate buildings for wind design using this. So Dr. Seymour Spence at the University of Michigan and some of his students put together a software, effectively, called WIRA, which does this reliability analysis. So rather than here we ran 5 wind angles, they run tens of thousands. And they vary all sorts of different parameters of concrete strength, rebar strength, loading, and ultimately report a reliability that you're intending to now, in this case, this beta factor, they call it, to be less than the prescribed criteria. So it's been a very interesting process. We've been working with Dr. Seymour and his team, and we've learned a lot. We've learned that it's not so easy to just put it all in a software and get an answer. So there's still more work to be done here, but there is a lot of opportunity for how this approach could be used in building design in the future. And along with that, there's a lot of other research going on throughout the country. There is some link beam research going on at the University of Los Angeles. Dr. Spence is at the University of Michigan doing more work on the reliability side and the wind tunnel side. There's composite steel link beams being tested for this process at Washington State University. University of Buffalo is also doing steel beam testing, and a variety of other universities are all doing more physical testing on different components of this performance-based wind approach. So with that, I'll end and see if there's any questions. Sure.
So in terms of detailing, the coupling beams, is it similar to seismic detailing where we have those diagonal confined?
No, so that was actually the impetus for doing some of the first research at UCLA, was we wanted to prove that just using normal detailing practices, that you still get performance and the behavior that will allow this modest nonlinearity. So the beams that were physically tested are just conventional, what you would normally see detailed in wind in non-seismic regions.
I have a couple of questions.
Sure, no problem.
So you mentioned that the rotations were not that significant. Right?
Yeah.
So was there a time that you had to go back and reiterate your nonlinear model to address that? Because it would have been like fully hinged, right? And you have to go back, tinker that a little bit somewhere.
Yeah, so in this project, no. We've subsequently been working on another one where we did have a problem. Because the response of this building, as I mentioned in one of my figures, is really what we call crosswind. The building's kind of oscillating back and forth like this. So any nonlinear behavior kind of gets reset as you go back. The other building that we were looking at was really more of an along wind response. So it's getting pushed over and kind of just constantly pushed in that direction. And we found with the term that we like to use is ratcheting. It's ratcheting further and further. And in that case, we actually had to go back and revise the beams and make them stronger to kind of avoid that ratcheting behavior. Right, exactly, yeah. And they were all going in the same direction as opposed to the resetting. I mean, earthquakes, typically an earthquake, you kind of get the motion back and forth and it kind of is resetting. In wind, depending upon the behavior, it's not that way.
Last question. Before this performance-based design completely evolves, do you or your team recommend using some kind of a load increase factor for the wind load? Because what we are seeing is between the wind tunnel testing and tile histories and then the code recommended loading, it looks like there might be some factor where we can use and maybe avoid being this much.
I'm not sure if I fully understand.
What I meant is code underestimating the loads?
In some cases, yes. And that's why we do wind tunnel testing, because in some cases, in particular, like the US codes do a very poor job of estimating dynamic behavior, crosswind effects, as opposed to there are other codes out there in the world that do a much better job of trying to capture that crosswind effect. So when you get taller and taller, that becomes more of a driver, and that's really why we recommend and do the wind tunnel testing. So we really feel, I mean, there's been some jurisdictions out there that we've talked to that have been a bit resistant about this approach. Even though in some of those jurisdictions, I could actually not even do a wind tunnel test. I could do an 800-foot tall building and not do a wind tunnel test, even though I know that's not the right thing to do, and just design to code, and they would be happy because you designed to code. Even though I know the loads are higher than that probably. So this is a methodology to do better engineering, right? I'm going to do wind tunnel engineering. I'm going to apply a thoughtful procedure if I had to minimize the impact. And we'll see where that goes with some of the jurisdictions we're working with.
Sean, thank you for a very good presentation. 2 questions. What was the speed of the wind that you had as a peak in your 1-hour wind event? And what's the approximate return period for that wind event?
Yeah, so for a building of this classification, we do a 700-year return period. So the windstorm that happens once every 700 years. And in Austin is just kind of on the border of being impacted by hurricanes. You know, Houston is closer to the Gulf, Austin's a little bit further in. So the wind speed that we use there is 105 miles an hour for that evaluation.
Thank you.
Performance-based wind design, the performance is the same as the seismic. So I want to know the discussion in the committee. So that is based on, for example, category of the load control methods and also the displacement control methods. This is very similar to the conventional seismic design.
Correct.
Okay. Because the displacement is very limited. So
Yeah.
force control method can be extended other than the displacement.
Yeah, I mean, the methodology is very similar to performance-based seismic design. The acceptance criteria is very different. And that's just how we've evolved as engineers. We accept major damage in earthquakes. We're just trying to prevent casualties, deaths, right? Whereas in wind design, traditionally, for a very big event, we say, no damage at all, nothing. There's a disconnection right now between how we design buildings for earthquakes and how we design buildings for wind because of that difference in acceptance criteria. And we're trying to bring it one step closer. We're not getting all the way to how seismic is yet, but it's one step closer.
Just a short question. So the pre-standard is covered for modeling or analytical procedure for the damage analysis for wind design?
Yeah, there's recommendations in that pre-standard for how to do the analysis. I'll say they're pretty high level. They don't get into the details of like the backbone curve hysteresis that I presented. That's not covered yet in any of the guidelines because we're still learning and researching. But actually right now downstairs, ACI 318W is meeting. And that is a subcommittee that is writing an appendix to ACI to put in a lot of these details into the code. So they're actually trying to take this process and make it more formal, not part of the code as an appendix to the code, but it has more of the guidelines on some of the more technical aspects.
How about time step? Is it established?
Yep, that time steps in the pre-standard, yeah. And you can get this available, it's free online. So if you go to ASCE, you can find it free online.
Thank you.
Just one point you just mentioned, isn't there really a fundamental difference between the wind loading and seismic loading? And of course, with wind loading, you have basically an applied load, right? So you can't have very high damage levels, where in the seismic application, you have the inertial response severity in that way. So you can't go there, right? They have to be different.
I fully agree they have to be different. You know, what I was mentioning a minute ago about the crosswind response versus the alongwind response, we're learning more about how that'll impact this, right? And so actually the Koreans right now are investigating this process. There's some researchers there, and they're putting it in their code. And they have actually a little bit different approach than this pre-standard approach where we have this demanded capacity limit of 1.25. They're actually doing it differently, and they're taking they're doing like an R factor approach, sort of similar to seismic, but the R factor only applies to the dynamic component. It only applies to that resonant crosswind component, and it doesn't apply at all to the long wind component because of essentially what you're saying. So there's a lot more that we're learning, and we're going to be continuing to evaluate this as we go.